3B, I believe it was number 27, that talked about the derivatives of some polynomials and then said to use linear algebra for that one. I was struggling to get started on that one.
Okay, I think I just responded to you on that one in the, the DQs. I haven't been able to go through all the DQs, but that's a good one. And I didn't actually give you an answer. I just gave you a hint. First of all, remember that what you're looking at is polynomials, right? And so when you're taking derivatives and stuff, they can only be certain things, right? It's not like like you take a derivative of sine, you get another sine function, right? So it can kind of go on forever, right? But when you take derivatives of polynomials, they decrease in degree, right? So they're kind of special in that sense. So my hint was, consider the map from the, so pretend your polynomial you're trying to hit, p, right? Suppose that is a nth degree polynomial, okay? Consider the map from the n plus 1 degree polynomials to the n degree polynomials, right? Defined by q gets mapped to 5q double prime plus 3q prime, right? And so is that a linear map? And, you know, anyone can answer that. Yeah. So let's see. I forget, you're going to have to leave early today, right?
Correct. Yeah. Okay. I'm also still currently driving because I was heading home and then traffic, so that's why I don't have my camera on.
Oh, okay, so I was going to say you probably can't see if I share a screen, but with everyone else, I'll go ahead and share the screen, and then we'll get this filmed anyway. So the question is to show that use linear algebra to show that whoops, let's change colors. Like for any p, let's see, sorry, I have to keep letting people in too. For any p in pf, so these are just polynomials with you know, coefficients coming from the field f. There is q in pf such that 5q double prime plus 3q prime is equal to p. Okay, so, and it says use linear algebra, right? So you're supposed to do something with linear algebra, not just differential equations. Now, of course, these are all polynomials, like I said, right? So like that. So my suggestion is, without just totally giving it away, is to look at, whoops. So, okay, sorry. Suppose p is an nth degree polynomial, right? And so those derivatives, if I'm going to get something of degree n, need to come out from n plus 1 degree polynomials, right? So I want to consider this function f going from p n plus 1 of f. F is just the reals are complex, right? To p n f, like that. And what it's going to do is it's just going to implement that function there. F of q is equal to 5q double prime plus 3q prime, right? Okay, so is that a linear function? How do we show it's a linear function? This is just a good like place to start anyway. So what would I need to do to show that this is a linear function? Okay, so let's come
to actually take the derivative here.
Well, no, let's come over here and do the notes at the same time, right? So,
okay.
So I've done these notes in such a way that you can, like, I gave you a PDF copy too. Basically, these are a lot of the theorems from the book, and you can fill out these things if you want, right? So you have this PDF file, and then I also gave you a web version of this thing too. So what does it mean to say that f from v to w is linear?
And it holds under addition and multiplication.
So say that again. It does what?
Holds under addition and scalar multiplication.
Okay, so one thing we do want to do in the class is be real careful about the way we say things. So what do you mean by holds under? It's not quite the right words. You've got the right idea, but what is the right words?
I don't know.
So what does it do? I mean, in terms of symbols, right? Okay, or does anyone else? Is there a good word like if I add two vectors and I apply L to it, what happens?
Isn't
to
it
the result?
closed? That the vocab you use instead of holds?
It's not closed either. It's not quite. That's not quite the right word either. Suppose. Let's see. What's a good one? Like suppose I'm looking at the exponential function, right? So sorry, I'm going to leave this problem we were on for just a little bit. Suppose I'm looking at the function f of x going from r, the set of all reals, right, to r plus. So the set of real, in fact, the open interval is 0 to infinity, right? And the function is going to be f of x is equal to e to the x, right? Like that, okay? So r plus is a subset of the reals, right? So I could view this as a function from r to r. Is this actually? This is a great example. Is this function linear? Where I'm thinking of r on both sides as having plus. So R is a one-dimensional vector space over itself, right? Everybody should shake your head there, right? So, I mean, our basic vector spaces are things like Rn, right? So don't forget R1, which is just R, right? It is definitely a vector space over itself, right? So the vectors are reals and the scalars are just reals, right? So that's a sort of a basic, super simple example. So here I've got a function going from R to R, right? Is it linear? Thinking of the reals as, R together with, so our set is the reals, plus is just plus, right? The scalar multiplication is just times, right? And then we've got 0, right? All vector spaces have a 0, so it's got 0, right? So is this linear, right? This is a question you ask, high school students, right? What would it mean to say it's linear? I would have to say f of x plus y is equal to what? If it were linear, what would I have to write here?
F of x plus f of y.
F of x plus f of y. Is that true? Is it true that f of x plus y, which is e to the x plus y, is equal to e to the x plus e to the y? Better. Exponentiation is definitely not linear in this sense, right? This is sort of a very non-linear function, right? Okay. I guess a more common one for kids to mess up is like squaring, right? If f of x was x squared, right? Or square roots, right? Things like that. Now this is tricky, right? Suppose I consider this, and I think one of you had this as an example. Suppose I consider, so on one side I have r, and I have r with, so it is still the reals. So the vector space, reals plus 0, and then the scalar multiplication is usual scalar multiplication, right? On the other side, I have the interval 0, 1. Sorry, it's not 0, 1, 0 infinity, right? But now I'm going to say, so this is what I called R plus. I'll just call it R plus. So now my vector space is going to be R plus. So the positive reals, not including 0. But now the addition, so to speak, is going to be multiplication, right? And the 0 of this thing is going to be 1, right? And what is scalar multiplication going to be? So now I've got this problem of having the same thing used for 2, so maybe I'll write it as actual multiplication like that. So then the scalar multiplication will actually be, exponentiation. So it'll be like alpha scalar multiple r, right, will actually be, r to the alpha. Right. I think that's what I want to say. That's what I want to say. Yep. That's what I want to say. Who had this problem? Someone had this problem. Or did no one have this problem? Well, so this is a great problem then. Is this a vector space? So here, let's do a little review first. Is this funny thing here a vector space? And I know Austin, you've seen this because I definitely did this in 345. That's a long time ago, but you've definitely seen this before. So is this a vector space? Like, is it true? Like, what do I need to check? Let's just check a couple of things. But like, if this is supposed to be a vector space, what do I have to check? What is something I have to check?
Scalar multiplication.
So what do I need to check? I mean, there are like these 9 axioms, right? So like, we don't want to check them all. Just give me a couple.
Closed under addition.
There's no closure here because, this is just the space, right? We're not looking at a subspace. We just have the space, right? So we're not interested in closure. I mean, okay, maybe we are, but definitely the positive real numbers are closed under multiplication, right? That's certainly true. So it's not the closure, but, assuming that you're in a structure, right? So the general setting was like this. I have a vector space, I have a plus, I have some sort of 0, and maybe even say of the vector space, right? And then we have this kind of scalar multiplication, right? And the scalar multiplication has something to do with whatever the field is, right? Okay. And then there were some axioms. And so one of the axioms is what? Okay, there's a bunch of you here. I'll just get Drina, give me one axiom for vector space.
Associative?
Okay. Yeah, so that'll be for addition, right?
Yeah.
So there's like, we'll have V1 plus V2 plus V3, right, is equal to V1 plus V2 plus V3, right? So we'll have something like that, right? So that's like an axiom that needs to be checked, right? Okay, so let's try checking that axiom, right? So I'm saying my vectors, just under multiplication, is it true that R times S, because the plus now is times, right? Times T, so these are all positive real numbers, right? Is the same as R times S times T, is that true? Come on, is multiplication in the real numbers associative?
Yes.
Yes,
Yes.
right? So it's definitely true, right? Okay, so, and so you go through and you check all those axioms, right? And basically they hold for this funny structure here because they hold for multiplication in the positive numbers, right? Let's check that the thing I'm calling 0, which is 1 here, is actually behaving right? So I need to check that V plus, in the sense of V, the 0 of V, right, is supposed to be what? It's supposed to be V, right? And it's also supposed to be the case that 0V plus, in the sense of V, right, vector V. I've got V's, this is the vector space V down there, right? So, I mean, this was one of the axioms, right? But I have this thing that when I add 2 other things, I just get that thing back, right? So now remember that this plus is becoming times in the reals, right? And the 0V is becoming 1, right? For this vector space, right? So is it the case that R times 1 is equal to 1 times R is equal to R? Okay, what do you think? So given that R is in my space here, so in the space R plus, what do you think minus R is in the sense of this vector space? It's got to be the inverse with respect to this, right? With respect to multiplication and 1. What's the inverse of R with respect to multiplication and 1?
It would have
Right.
to be -2, wouldn't it?
I'm looking for something, right?
Mhm.
Such that when I multiply it times R gives me 1, right? Remember, we're looking for something so that when I add
additive,
it,
is it the additive inverse?
I'm trying to figure out does this set have an additive inverse? That's the question, right? So this is the axiom, right? Okay, but in this case, the plus is times and the 0 is 1, right? So given any positive real, is there an S, a positive real, such that S times R is equal to 1?
It's reciprocal?
It's reciprocal, right? So the additive inverse in this vector space minus R in this vector space is really 1 over R, right? Or if we like R to the -1. right? If you feel like this feels strange, I would say really understand this example, because the next course you're going to take is abstract algebra, and it's all about this kind of stuff, right? So I mean, you got to drop your favorite notion of plus and times and 0 and 1 and generalize that a whole bunch, right? So, but this turns out to be a nice example. Okay, so this structure, right? So we're looking at R plus times 1, and then my funny scalar multiplication, which I don't really want to write here. Again, I guess maybe I should stick with the times like that so I can do that. All right, is going to be basically exponentiation, right? Okay, so what is one of the axioms that I need to prove with the scalar multiplication?
Distributivity.
Okay, so distributivity, right? So that would look like alpha. So in our usual setting, it would be alpha, and then this is the scalar multiplication of v, right? And then I've got two vectors, v plus in the sense of vu, right? I'm doing this in this case because we have this strange sort of addition and multiplication here, right? And so this should be alpha v v. Again, these are vectors. This is just indicating the plus of the vector space, right? Plus alpha, and then this sense of v, u, right? And I need to decorate this with a v there, right? So that's one of the axioms, right? That distributivity, right? Right? Everybody shake your head, right? That's one of the axioms, right? Okay, so changing it into our current notation, right? This is going to be, so what is this? So this becomes times, right? So I'll just, it'll be, well, I'll just do it, right? So these two things are just positive reals. So instead of writing u and v, I'm going to write r, the plus is s, I'm sorry, the plus is times, right? And then the u is going to turn to s. This scalar multiplication, remember I said, was just exponentiation, right? Okay, so is that the same? So what is this side going to do? So this is going to be r to the alpha times s to the alpha, right? Because this plus turns into this times. Alpha dot v is v to the alpha. Alpha dot u is u to the alpha, right? So it turns into that. Okay, so is this true? It's not true, Austin. Doesn't exponentiation behave like this? I think it does, right? I think this is true, right? And this is true for any alpha at all, any real at all, right? Alpha could be -1, it could be 0, it could be anything, right? So this is anything from the field of reals, right? Okay, and the other axioms are proved similarly, right? So if you're not following this, I would strongly suggest you go through this argument, right? So again, the thing we're showing here, and I thought someone had one of these. I'm sure someone had one of these to do. Maybe that person didn't, or whoever those people were didn't turn it in. So we're looking at R plus. This is just the positive reals, right? The addition in this vector space is multiplication. And I keep wanting to write, I like dots, right? So the addition is multiplication. Normal real multiplication, right? The 0 in this vector space is 1, right? And then the scalar multiplication, which I'll just write as dot here, is going to be exponentiation. So just sort of translating, this turns into the plus of v, right? This turns into the 0 of v, right? This turns into the scalar multiplication of v, right? And then this is, just v, right? So whatever axioms we have for this, we need to show hold for that structure right there. Okay. And we've done a few of them, right? We haven't done all 9, but we've done a few of them, right? Okay, are we clear on this? It's a great example of a vector space that's a little bit weird. It's an easy one. It's just the positive reals with multiplication. So that's kind of trivial, right? So that's an easy one in that sense, right? On the other hand, it's sort of weird, right? Okay. Now the question is, So going back to my function f of x is equal to e to the x, right? So if I view this f as a function from R to R, where both of these are vector spaces over the usual vector space with plus, right? So if I view it as like to make it clear, if I view it as a function from R plus 0, right, and then the usual scalar multiplication, right, to the same structure, right, R plus et cetera, right, then it is not linear. Right? We saw that way at the start, right? But what if I view f as a function, same function, e to the x, right? But now it's going from, r plus 0 and the usual, I'll just write it like this, like alpha r, right? I mean, so it's just multiplication, usual multiplication for a scalar product, right? But now it's going over here to this sort of weird version of things, so r plus. But now instead of plus, we have times, and instead of 0, we have 1. And now instead of alpha times r, it's r to the alpha. Right? So this is this new vector space we just looked at, right? So now is it linear, right? So now is it the case that f of x plus y, right? Well, what is that? That is e to the x plus y, right? But that is e to the x times e to the y, right? And that is f of x times f of y, but this is the plus on this side, right? So it's the plus of that vector space over there, right? So it does satisfy that, right? It takes this thing and moves it to that thing, okay? But this is really the plus of, this funny vector space. All right, and what about the scalar multiple? Is it true that f of alpha x, what needs to happen? It needs to be alpha f of x, right? Okay, well, is this true? So f of alpha x is e to the alpha x, right? But that is e to the x to the alpha, right? But that is the scalar product of alpha on e to the x in this funny vector space, right? Okay. So what happens here is we actually get that the exponential function is linear, right? When you define the right algebraic structure for the reals on the right-hand side, right? Can you think, with this in mind, can you think of a linear inverse I'll just write this like that. And then the usual alpha r, right, for what would be the inverse? Linear inverse map right here. Not hard to guess. The map is e to the x. What is the inverse of e to the x?
Would it be natural log?
It would be natural log. Yep. Right. So natural log of x, right, will map positive numbers, right, to all real numbers, right? Think about the graph of natural log, right? It looks like, like this sort of, right? So it's mapping, it's mapping this side over here, positive numbers, to all real numbers, right? And it's the inverse of e to the x, right? And it satisfies all these same things, right? With the right sort of notion, right? So, the g of xy, right, which is ln of xy, right? What does that become? It becomes ln of x plus ln of y, right? So it's taking the sum in the domain space, right, to the sum in the range space, right? So this is probably a new idea to you, right? So you can think of the natural log, which is a very, you can think of exponentiation and logarithms as actually linear maps, right? When you choose your vector space correctly, right? Which probably feels a little bit strange. It's worth reflecting on a little bit, right? It's a very simple example that's kind of interesting, even though it's as simple as it is, right? There are really interesting, complicated examples, but this is a really interesting, simple example. Okay. Okay, so going back to this little set of notes, what you want to say about a linear map is not that it, I forget what the words people were using were, but you want to say that linear maps preserve the operations, right? They preserve addition, they preserve scalar multiplication. That's what you want to say, right? So writing it down in sort of math, right? You say L of V1 plus V2 is L of V1 plus L of V2, right? And you want to say that L of alpha V1 is alpha L of V1, right? So those things have to happen in order for the map to be linear, right? If you're going to show that a map is linear, you have to prove that both of those things happen, right? So if you're given a map and say, prove that something's linear, you got to show those two things, right? So we'll come back to that problem we were looking at initially in just a minute. But one thing you want to notice right off the bat is what has to happen to 0. So what if we have a function that, so we have L going from V to W, right? L of the 0 of V, does it have to be the 0 of W, and why? Why or why not, right? I guess I'm hinting at why as the right answer. You guys have to participate some. You have to say stuff. How can I get 0 of V from an arbitrary, say just, I hand you an arbitrary vector. How can I get 0 from, how can I make 0 from that vector?
You multiply it by 0?
I can multiply by 0, right? We had that as a theorem last time. 0, the scalar 0 times V is always 0, right? So if that's true, then L of 0 times V, well, what is it? It's 0 times L of V, right? Okay, but this 0 times V is the 0 of V, and this 0 times L of V is going to be the 0 of W, right? Okay, so the 0 also has to be preserved, right? Okay, it's also true that the inverses have to be preserved. Same kind of argument, right? So you don't have to show that the inverses are preserved. You don't have to show the 0 is preserved. You have to show these two things here. Okay. Going back to that example, right? I was saying define a function f going from the n+1 degree polynomials to the n degree polynomials, right? By f of q is equal to 3, no, maybe it was 5 q double prime plus 3 q prime, right? Is this linear? So now we know how to answer that question. If I'm going to show this is linear, I need to show two things, right? So what two things do I need to show? I need to show that f of q1 plus q2 is what?
F of q1 plus f of q2.
Yep, f of q1 plus f of q2. And that's exactly something we prove, right, in, calculus classes, right? I mean, you have to do, we are talking about derivatives, so there's a little bit of use of actual calculus here, right? So f of q1 plus q2, whoops, right, it's going to be 5 q1 plus q2 double prime plus 3 q1 plus q2 prime, right?
I have a quick question.
Yep.
I'm sorry, I think I might have missed something. Where did the 5 and the 3 come from?
Oh, that's just part of the problem. So this is 3,
oh, okay,
this is
I'm
3C number 20 something, 29 maybe.
Okay, thank you.
So Q1 plus Q2 double prime, that's the same as Q1 double prime plus Q2 double prime, right? Because differentiation is a linear function, right? Right? That's one of the things we teach in calculus classes, right? I mean, one of the things we teach in calculus classes is that df plus g is df plus dg, right? Or if you like, you know, f plus g prime, I'm trying to make it look like an operator, right, is f prime plus g prime. It's a basic calculus thing, right? And we prove that d alpha f is alpha df, right? Or if you like, you know, alpha f prime is alpha f prime, right? So what's that saying? It's saying that the differentiation operator is linear, right? That's exactly what it says. And if you're unfortunate enough to be in my calculus class, that's actually how I say it, right? So the primes just go through, right? So this is f q1 double prime plus, you know, sorry, not an f5, q2 double prime, right? The, you know, the 5 passes through, you know, 3q1 prime plus 3q2 prime, right? We can gather up those terms and I can get 5 q1 double prime plus 3 q1 prime plus, now I'm running out of room, oops. I'll stretch this over for a second. Plus 5 q2 double prime plus 3 q2 prime, right? Make a little barrier there, right? So but this is just f of q1 plus f of q2, right? So it preserves additive. It preserves the addition, right? Okay. Does it also preserve scalar property? Of course, right? So, you know, f alpha q, right, is alpha q double prime, no, 5 alpha q double prime plus 3 alpha q prime, right? But that's clearly the same as alpha times 5q double prime plus alpha times 3q prime, right? And that's alpha 5q double prime plus 3q prime, right? And so that's alpha f of q, right? So that function f going from the n plus 1 degree polynomials to the n degree polynomials, I'm going to leave off the f there, say it's just the reals, right? And remember the function is just taking q and mapping it to 5q double prime plus 3q prime. It's linear, right? So now how can I show it's onto, right? We want to show that p, you know, any p from here is one of these things. How can I show that a linear function from one vector space to another vector space is onto?
Can you define onto?
Yeah, it means
that the same as surjective?
Yep, surjective.
Okay.
Right.
Isn't it if it spans the second space?
So something will have to span. So the image would have to span, right? So that's true. But now I'm thinking there's a certain theorem in your book that should have stuck out as being exceptionally important, right? Because it's got the word, anytime you see a theorem with the word fundamental in it, right, you should think, oh, that's really important, all right? Okay, so what does the fundamental theorem of whatever linear maps tell us about? These are both finite dimensional vector spaces, right? So what does the fundamental theorem of linear maps tell me about this situation here?
Is the fundamental theorem that the dimension of V equals the dimension of the null T plus the dimension of the range of T?
Yep, so in this case, it's the dimension of P n plus 1, right? Has got to be equal to the dimension of the null. By the way, I write kernel most of the time. And this is f here in this case, plus the image of f. And your book calls it range, right? So maybe I should make that clear, right? So kernel equals null in my book, and image equals range. Okay, and they're all common. Kernel's more common, especially later on, but for some reason this book loves null, and it loves range instead of image. But they're both common. Good. And what do I want to show? I want to show that anything in the range can be hit, right? So my real goal here, and by the way, I should have dimension here, the dimension of the image of F, right? I want to show the dimension of the image of F is actually the full dimension of Pn, right? Because that means everything will be in the range, right? And what is the dimension of Pn? Let's just make sure we get that right. So those are all polynomials less than or equal to degree n, right? Okay, so what's the dimension of Pn then? What's the dimension of the space of polynomials of degree n?
Would it just be n?
Or
n plus 1?
n plus 1, right? So this is n plus 1, this is n plus 2, right? So I would be done if I could show that the dimension of the null space of F is 1, right? Okay. So that's what we're going to do. We're just going to see what is the null space of F, right? So for what Q is it the case that F of Q, and what is the null space? Those things that get mapped to 0, right? So for what Q is F of Q equal to 0, right? And now we do have a little bit of calculus to do. So this says, 5Q double prime. I mean, this is a high school calculus problem now, right? Q prime equals 0, right? So if I integrate both sides, what happens on this side? What's the integral of Q double prime?
Prime.
Q prime, I think someone said it, it's 5Q prime. What's the integral of Q prime? Q, right? Okay, and then of course we have this sort of all important, integral constant, right? So equals C, there's some sort of constant, right? So this is what I know. Now remember, these are polynomials. These aren't arbitrary functions, they're polynomials, right? And so I know the degree of Q prime is less than the degree of Q, right? So I know that, right? And the sum of these two things is just a constant. So what do I actually know about Q? Maybe someone's chatting. I can't tell. What do I actually know about Q?
Isn't Q have the higher degree that will never equal the cancel out to equal the constant? So your null has to be 0.
The null doesn't have to be 0, but yeah, I mean, but these are polynomials, right? So whatever this Q is, I mean, suppose it was an x to the n plus, an minus 1, x to the n minus 1, etc., right? So some nth degree polynomial, right? So this is Q of x, right? And then this is the derivative, so it's going to be 1 degree lower than that, right? And the sum of those two things is going to be some constant, right? What does that tell me about the degree of Q?
That it's 1.
That it's 0, that it's got to be a constant, right? So Q itself has to be a constant. I mean, Q has to be basically this constant, right? Its derivative will be 0 and it'll be that constant, right? I mean, Q can't even be like this. Q of x can't even be ax plus b, right? It can't even be linear, right? Because if it was linear, then this thing up here would be 5a plus 3ax plus b equals some constant, right? But that's not true, right? I can't have an x there at all, right? The only possibility is that Q is actually itself constant, right? So what that tells me is that the null space, right, the set of Q's where this happens, so the null space of this F is equal to constant polynomials So that's just a set of C such as C is in R, right? If you like, right? Constant polynomials, right? What's the dimension of this null space? It's just basically R, right? So what's the dimension of R as a vector space over itself? This is not a trick question. This is the easiest question you could possibly ever be asked. Yeah, it's 1, right? The dimension of the reals over itself is 1, right? A basis would be like any non-zero number, right? Because I can reach, any non-zero number will span because I can get everywhere else by multiplication, right? So we have what we want, right? Because this is 1, right? So again, just sort of rewriting this, we have the dimension of Pn plus 1 is equal to the dimension of the null space of F plus the dimension of the image of F. We just showed the dimension of this is 1, right? The dimension of this was n plus 1, right? The dimension of this was n plus 2. Oh, sorry, we don't know the dimension of this. This is what we're trying to get, right? We don't know that, right? So what we get here is we get the dimension, whoops, we get that the dimension of the image of F is equal to n plus 2 minus 1, right? So how do I know that every polynomial can be hit? How do I know that f of q equals p for every p in Pn? For some q, there's some q. Because that's what the image is, right? These are the things in the image, right? And the image has degree n plus 1, right? If I'm looking at nth degree polynomials, and I've got a subspace of dimension n plus 1, do I have all of them? I have all of them, right? Okay. So whatever p is, I've got it, right? So we didn't actually solve anything. We didn't find some q that hits p, right? We didn't do that sort of thing. You could do that with calculus, right? You could just do that by brute force, right? But instead we use this sort of fundamental theorem of linear maps, right, to show that everything was hit, right? When you do it more advanced differential equations, you've got to use this kind of technique, right? You've got to use these sort of algebraic techniques. Okay, so that was a long time on a problem, but that's a good problem. It introduced a lot of stuff, right? Okay, good. Okay, so any other questions, right? I mean, I can do questions all night. Otherwise, I can keep talking about, go back and talk about theory.
So just to clarify, with this problem, we just need to prove that it is onto or surjective to say that there exists?
Yep.
Okay.
And to show that it's surjective, you just need to show that the dimension is correct, right? In this case, yep. So that's really where you're using the linear algebra. That's where the linear algebra is being used, right? Good, okay. Okay, so we know what linear maps are now, right? Well, oh, I know who just disappeared, okay. So let me just get a snapshot here of who's here. Only Hannah has left, right? Everybody else has been here, okay. Sorry, just give me a second here. Okay, so yeah, any other questions? Otherwise, I'll jump into just looking through these notes. No? Okay, I've looked at a lot of your DQs. I haven't had a chance to look at all of them yet. Yeah, go ahead, Grace.
Oh, I was going to say, I have a quick question about the notes. Will you post the filled out notes, or are you just posting the template?
I mean, I'll post this video so you can see that, and okay. I can save them. We'll see. I'm not even sure how far we'll get. Okay. And there's nothing here that your book. This is sort of like just taking the things from your book and condensing it, right? And then I think the benefit for you would be if you filled them out, right? That would really be kind of the benefit. Okay, so we know what linear maps are. We actually get a new vector space from our linear maps, right? So now this is sort of a extra level of abstraction here, right? So when we look at our linear maps, so the set L from V to W, right, is actually the set of all maps going from V to W, so that L is linear. Right? And it turns out this is actually itself a vector space, right? So I can take two things in there. I can take an L1 and an L2 in this space, right? And I can define L1 plus L2, right? And so that's going to be a new thing, right? And so how am I going to define this? I will define it, on an input, which would be something from V, right? Because these are going to be functions from V to W, right? And of course, you do what you would obviously do. You do L1 of V plus L2 of V. All right. And you're going to define alpha alpha L1 of V, right? You want to get the parentheses in the right places here, right? And that's going to be the way you're going to define it, right, is as alpha L1 of V, right? So kind of the obvious things, okay? And then what do you need to prove? You need to prove that, well, this is linear, right? When I add these two things together, I get something linear, right? So here we are sort of proving closure here, right? So I need to show that when I add two of these things together, it's linear. When I take a scalar multiple, it's linear, right? What we're actually doing in some sense is I could take any vector space W and I could look at all the functions going from X into W, where X is any set at all, right? And define addition and scalar multiplication the same way, right? And actually that's a vector space already. All right, so this part, the domain part, doesn't even need to be a vector space, right? Nothing I did here actually uses the fact that the domain is a vector space, right? Until I start trying to show that this combination is linear, and then of course I'm looking at algebra going on the V side, right? Okay. So that's not a full proof, right? But that's sort of the hint, right? So that's, basically we got closure. If I knew already that this was a vector space, then that sort of does it, right? Because then we're proving that it's a subspace. And we know that to prove it's a subspace, we just have to prove closure, right? So that's the thing we need to prove. Okay. When V and W are the same, right, the notation is just LV, right? So those are also called the operators on V, right, or linear operators. Okay. So most of the time in this class, context will determine that something's linear or not. So usually when I write something like L from V to W, I won't necessarily say that it's linear. That'll be an assumption, right? And we're really only mostly interested in linear maps in this class. What's some examples of linear maps? And your book actually has a bunch of good examples of linear maps. So this is section 3.3. So let me just find that real quick. Let's see, let me stretch this back over this way. No, before that. Actually, let me do it this way. Yeah, I mean, just right here, right? There's a bunch of good examples right in this section. So page 53, at least in this version, right? Page 53. This is the latest version that's online. What are some examples? So one example we're going to need is the identity map, right? The identity map is definitely linear. Okay. How would you show that? You would say, look, the identity map of V1 plus V2 is V1 plus V2, and that is the identity map on V1 plus the identity map on V2, because it's just not doing anything, right? So it preserves addition. Similarly, it preserves scalar multiplication, right? What are some other good examples of linear maps? I want everyone to give me an example. So Drina, what's an example of a linear map? just go around.
An example of a linear map.
Yep.
You put me on the spot and my mind went blank.
I did.
Yes.
So you get to go first. So you should have the easiest challenge here, right? So well, except other people can look while you're answering. But think calculus. Can you think of a something that's linear in calculus?
I mean, a polynomial of degree 1. Or do
Let's
I need a
see.
more specific?
Oh, we can do that. Okay, but you have to be really specific now. So so not quite a polynomial degree 1. Like, is it true that ax plus b, and this is a good thing to think about actually, is that linear? Like, is it true that f of x1 plus x2 is equal to f of x1 plus f of x2? Or is there even an easier way to see that it's not linear? Because what is a linear? Yeah, go ahead. Go ahead, Grace.
Oh, would it not be linear? Because if we plug in 0, we're not going to get 0, like we would get whatever b is.
That's right. To be linear, 0 has to go to 0, right? So this is too general. Can we make it a little bit simpler and get something that is linear?
Ax?
Just ax, right?
Mhm.
Okay. So so we'll attribute that one to Drina. Okay, so just a multiplying by a scalar, right? That is a linear function. What's that a linear function from? That's a function from R to R, right? Okay. I mean, maybe that's worth. I mean, maybe it's actually worth checking, right? I mean, so just to make sure, right? So if I put in x1 plus x2, yeah, I guess so. Everyone should tell me what the domain and range is that you're giving me too, right? But this is going to be, ax1 plus ax2. Whoops. And so this will be ax1 plus ax2, right? But that is f of x1 plus f of x2, right? And then so it's definitely preserving addition, right? And f of alpha x, right, is going to be a alpha x, right? But that's alpha ax, right? And so that's alpha f of x, right? So it preserves scalar multiplication. So that's good. Okay. Joseph, you next. Give me a linear transformation. Give me the vector spaces, the domain and range too.
Wouldn't you just be able to increase the degree? So like ax squared?
Well, let's see. Would that be true? So ax squared. And these are, yeah, it's good to play with this, right? So let's pretend that was our thing, right? So is it true that f of x1 plus x2, so now this is going to be a x1 plus x2 squared. Is that the same as f of x1 plus f of x2, right? Which is a x1 squared plus ax2 squared.
I feel like
I
that'd
mean,
be
I'm
not
just
the same.
asking. That would be not the same, right?
Yeah.
In general, right? I mean, at least for the reals, right? If we had fun and went to the fun little field of Z2, then it turns out this nice thing is true, right? but in general, it's not true. So yeah, increasing degree is going to become nonlinear, right? I mean, a quadratic is not linear, right? So that's kind of, a hint, right? So what's something else?
Differentiation map.
Okay, well, it wasn't your turn, but it was the differentiation map. What is the domain? I'm going to come back to you, Joseph. Think. So what's the domain for your differentiation? So I'll call it D for differentiation. And what's the domain going to be?
On the reals. Real to real, I think.
So I don't differentiate a real. I got to differentiate a function, right?
Yeah.
There's actually lots of options for this, right? So I guess I'm trying to get you to pin it down. So what is it I'm differentiating, and what is the output? Like, give me an example. What is a sample input?
No?
Huh?
A polynomial.
Okay, so you're saying like input something like x squared plus x plus 1. What is the output?
X1 plus the constant.
2x plus 1?
Yeah, sorry.
Maybe, right? And then so this is your what you're thinking, right? So what's like, if I apply it to sine, what do I get?
Cosine.
Cosine. It's important to know examples, right? So don't forget the math you're supposed to know, right? Because we need lots of examples for the class. Okay, differentiation is definitely a good one. But this isn't the only one. So I think what you're suggesting is we take D, and I'm going to go from the space of differentiable functions from R to R. I think this is sort of what you're thinking, right? And the output is going to be the space of functions from R to R, which I can write as, I guess the way I usually write is like this, right? Now, there's an interesting question as to whether or not the set of derivatives of a differentiable function have some interesting properties themselves. Like, are they continuous or something? Is it a better set of functions, right? That's not quite true, but they're also not just arbitrary functions, right? Like a completely arbitrary function is not the derivative of some function, right? So I could restrict this side some, but it's kind of complicated to say to what, right? What's a different thing you could have done? You could have said, well, I could be looking at like dA, right? Which would be more like, what is d dx at x equal to a of f of x, right? So at a particular point, right? And then my space on this side would be, so this dA thing, right? So over here, my domain would be, the set of all f, such that f is differentiable at A, right? And what is the output space? It's going to be going to, now when I take a derivative at a particular point, what is the output? It is the slope, right? So it's just a number, right? So there's a very different take on this same kind of idea, but the proof that it's linear and all that stuff is the same kind of proofs, right? That's what you do in a calculus class. Okay, Joseph, with derivative in your mind in calculus, what's another good linear function?
I guess then you could also do integration.
Integral is a great other. It's almost like the inverse, right?
Yeah.
Not quite the inverse, but something like the inverse, right? And so again, there's options, right? I could do integral as a function from integrable functions, whatever those are, right? That's going to be a topic of 571. What's the class of functions that are integrable in various ways? But in particular, if you had, say, continuous functions on a closed interval, those are integrable, right? So I might restrict to continuous functions on a closed interval, say like 0, 1, right, going into the reals, right? And those functions would be integrable, right? And now I'm thinking about doing things like the integral from 0 to 1 of f of x dx. In which case the output is going to be a real, right? On the other hand, I could think about, doing sort of the more formal integral, right? And we could restrict, say, to polynomials. And so I'm putting in a polynomial degree Pn, what would my output be?
Pn plus 1.
A polynomial Pn plus 1. Okay. And so this thing has dimension n plus 1. Now this is a linear function, right? So again, we know what? We know that the dimension of Pn plus 1, which is Pn plus 2, right, is going to be equal to the dimension of Pn, which is n plus 1. Oh, sorry, I've got this backwards. Dimension of Pn, whoops. Oh gosh, let's just erase this whole thing. What do I have? I have the dimension of Pn, which is n plus 1, right, is going to be equal to the dimension of the kernel, right, of the integral, right, plus the dimension of the image over here, Pn plus 1, of the image of this thing, the image of the integral function. So what is the kernel of integrals? When do I integrate something and get 0? When do I integrate a polynomial and get 0? As a polynomial, right? As the output. Yep. Grace?
Well, I was going to say when we integrating at 0, is that when we integrate a constant?
Not even a constant, right? If I integrate a constant, I get Cx, right?
Oh, right. I was thinking backwards. My bad.
Right. And by the way, I'm having to pick, to make this a functional, I'm having to say, choose the constant to be 0 or something like that. I'm having to fix a constant, right, on the side. All right. In fact, maybe I need to choose 0. I think that the only thing I can integrate to get 0 is 0, right? So this is so in the integral direction, this is a 1-to-1 map, right? Okay. Because the kernel is 0, right? And so the dimension of the image, right, is going to match the dimension of the input, which was n plus 1. So we won't hit everything over here, right? For example. Right. So you can use linear algebra and stuff like this. If we were doing differentiation, I didn't say that. What is the kernel of the differentiation map? Let's go back to that one again. Suppose I'm doing the differentiation, going from Pn plus 1 to Pn. What is the kernel of that map? Or the null space? So which things have derivatives that are 0? And this is what, yeah, so these are the constant functions, right? So these are the constants. Right, and so this is basically isomorphic to the reals, right? Or the same as the reals. So it's the dimension of that kernel is 1, right? Okay. What do you think the dimension of the second derivative is? The kernel of the second derivative? Which things get sent to 0 by the second derivative?
Polynomials of degree 1.
Oh, no. So, and its dimension is 2, right? Yeah, so things of the form ax plus b, right? Good. So you see there's a lot of linear algebra tied up in that sort of stuff, right? Okay. Good. Oh, let's see. I haven't even, we were still doing examples, but maybe we should. There's one really critical example. So you gave me this one, just ax, right? Going from r to, so this is basically going from r to r, right? So if I'm going from r into rm, what's sort of the corresponding one that's kind of like ax? What plays the role of multiplying by a single number and something like this?
Could it be the identity operator?
Well, so if these were different, it couldn't be the identity, right?
Oh, okay, okay.
So what can I multiply something Rn by? I'm going to multiply by something, right? And get something in Rm.
Like multiplying by x to the n.
So this is like a vector, right, in Rn. I mean, this is like, you know, classical vector, right? Classical vector in Rm, right? What do I multiply on this side by to get something over there?
A scalar?
Not a scalar. I mean, m and n may be different, right? I mean, this may be 5 and 3, for example. Let's just stick to it like that.
A matrix.
A matrix, right? And what size would the matrix have to be?
N by n.
Yeah. So if this was 5 and 3, right? What would it have to be? How many rows would it have to have?
Five rows.
So let's see if I had something like 1, 2, 3, 4, 5. How many columns do you think it has to have then? I've got a 5 and a 3 here. This is supposed to have 3 columns. Okay, so I'll just keep going. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? So there's a 5 by 3 matrix. And I'm going to multiply it here by x1 through x2, x3, x4, x5. Does that work?
Don't we need to have 5 columns?
We need to have 5 columns. And how many rows if I'm supposed to get something out here with 3?
3. Yeah, we'll just swap them.
Yeah, so we need a 3 by 5, right? Matrix there. Okay. So in our very simplest vector space, R to R, right? We have a constant times X is our sort of generic map, right? In the more general case, we're going from Rn to Rm, right? We do Ax, where now this is a vector from Rn, right? And the output is in Rm, right? And this is an M by N matrix. Right. But there's a lot of similarities between this multiplying by a scalar and multiplying by a fixed matrix. All right, they're kind of the same thing in some sense. Okay. Okay, so lots of examples of linear operations. So I'll stop there. Anyway, you can, you know, oops, what am I doing here? Fill in your favorite, you know, examples there. Okay, here's one of the most important properties of linear maps. See, is that quite fitting? I'm trying to get that in there. So I have V and I have W as a vector space. I have S is just some subset of V, and it's independent. Nope, still not fitting. Sorry. Someone used this in their homework already. And I've got so here's one case where I've got a set map instead of a linear map. So I've just got a function S going from, a function F going from S to W, right? So all I've got is I've got a vector space here. I've got a vector space here, right? I've got some vectors in here, V1, V2, VK, right? And I map them any way I want to over to here. Doesn't matter how. So this isn't V again. This will be W over here, right? And so this will be, you know, whatever F does. It may map 2 things to the very same thing, right? There may be, you know, VJ here might also go to exactly the same thing here. Right? So I'm just taking any set map at all. These are independent. Okay. Then there's a unique function that extends F to a linear map from the span, right? So that's what this is saying. There's a unique function F which extends this little f, which is completely arbitrary, to the span of S, right? Okay, so that's what this is. So what is the proof of that? What does an element of the span of S look like? So S is these vectors up here. What is the span of a set of vectors? No, you've all done your reading of these 3 sections. Last week we had 2 whole chapters. This time we had 3 sections, right? And I know the word span is in the section. So what is the span of a set of vectors?
Would it be a basis that you could use to make any of the vectors?
Doesn't being a basis doesn't really enter into what a span is. I got some vectors, right? I don't make any assumptions about them at all. They're just some vectors sitting there. Right? What is the span of this?
Set of linear combinations.
All the linear combinations, right? So all the things that look like this. Summation I goes from 1 to k, alpha I vi. And these alpha i's are just in the field, right? So the span is just a set of all the linear combination of those things, right? That's what the span is. Okay. Critical notion, right? This is just a critical notion. We talked a lot about independence last time, right? So a set is a basis, right? If the span of that set is everything and it's linearly independent. Span is just a set of linear combinations. Again, you know, with an eye forward to what's coming up, in the next class, you're going to talk about building lots of algebraic structures from elements, and there's going to be all sorts of variants of the span thing. So this is the very simplest case. And the theorem we're proving here is really, really special for vector spaces. Okay, the theorem we're proving here generally doesn't work. I can't take, if I have 2 things called rings, and I you know, I have a ring R and a ring S, whatever those things are, and I just pick some elements over here and map them arbitrarily into there. I cannot extend that to a structure preserving map. Generally, that's completely false, right? But it works for vector spaces. It's a very special property of vector spaces, as long as the set you have here is independent. So that's kind of the point of this thing here. And this thing is used all over the place in the book, and some of you even used it in your homework. Not sure if you knew you used it in your homework, or not homework, but in your DQs that you posted, right? And so what we need to see is we need to show that this works, right? So how can I take an element of this span? So first of all, is the span a vector space? There's lots of stuff to talk about here. So given a set S, so I got S subset of V. S is non-empty, right? So I'm not taking an empty set. Right? Is the span of S a subspace? If I take V1 and V2, what do I need to show for a subspace? I need to show that, you know, it's closed under addition and subtraction and scalar multiplication, right? So if I take 2 things in there, right, I add them together, is this in the span? Because I mean, this thing is just a sum of stuff in S. This is a sum of stuff in S, right? I'm taking 2 sums. It's going to be a sum of stuff in S. And that's not a formal proof, but that's a proof, right? I mean, to write it out formally, I may take this thing and say, well, this is summation alpha I vi. This is summation beta I vi. Right? So I put them together, I get summation alpha I plus beta I vi. Right? So I mean, that would be sort of a formal proof, right? But the idea is pretty clear. If I take a scalar multiple of something in the span of S, is it in the span of S? Sure, because I'm just multiplying by all these scalars anyway. It's just changing the scalars, right? Is 0 in the span of S? Sure, 0 times something is in there, right? So it's in the span of S. Is there anything else I need to check? Like, is -1 times something in the span of S? Yeah, so it's closed, right? So it's a subspace, right? So this is sort of the way you generate subspaces. Generally, is by taking spans, right? Okay. So if I wanted to find a map going from from span S into W, right? Remember, all I have is this little map going from S to W. How can I do it? How can I define f of summation alpha I vi, given that all I know is how to find f of vi? What's a sort of an obvious definition there? The goal is to be linear. So if it's going to be linear, there's really only one choice. And if I had this thing and it was linear, what would the answer have to be?
Would it be that f of the sum of a plus f of the sum of vi?
So say that carefully. So where do I put the sum?
So it would be f.
The f is on the outside right now. So where are things going to go?
Wait, let me see again. Wouldn't it be the sum of alpha plus the sum of?
Not plus. Where's the f going to go here?
Yeah. Let me rethink it.
Is it going to be on the VI?
Yeah, sure, right? I mean, that's linearity,
Okay.
right? That's what it is. You know, I mean, we wrote it like this: x plus y equals f of x plus f of y. Oops, sorry, f of x plus f of y, right? And then alpha f of f of alpha x is alpha f of x, right? But putting these two things together, f of alpha x plus beta y, right, what is that? It's, you know, f of alpha x plus f of beta y. That's using the additive property, right? And this is alpha f of x plus beta f of y, right? And there's nothing special about having two things here, right? If I have f of alpha 1 x1 plus dot 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 plus alpha n xn, right? And doing the same argument is going to give me alpha 1 f of x1. Right? Okay, so the way you think about this is over here I have a linear combination of the xi's. Right? That's a linear combination of the xi's, right? Everyone see that? You see that linear combination of the xi's? Everyone see that? Right? And you see this, it's a linear combination of the f of xi's, right? But it's the same linear combination because the coefficients are the same, right? So one way to think of linear functions is they move a linear combination to the same linear combination of f of the things, right? So a function is linear if it takes a linear combination of vi's and moves it to a linear combination, the same linear combination of f of vi's, right? So if my f is going to be linear, then it's got to have the property f of summation alpha I vi has got to be summation alpha I f of vi. There's no option, right? That's what it has to be, right? And if this thing is supposed to extend the little f, right, then this has to be summation alpha I little f of vi. No matter what that thing was, right? And that's got to work. So now the question is, does that work, right? So we're saying, look, what I actually have is I have f going from S to W, right? And I'm defining this f going from the span of S to W this way, right? That's how I'm defining it. Right? So is that linear, right? So that's the thing we have to prove. Is that linear? So we have to show that f of, take two things in the span. Right? So maybe I say v1 and v2. I need to prove that f of v1 plus v2 equals, f of v1 is f of v2, right? I mean, that's like, it's proving that it preserves addition, right? Okay, but what is this? So, well, the v1 is going to be like this. It's going to, summation alpha I vi. The v2 is going to be summation, beta I vi. Right? Because these v1 and v2 are in the span of S, so they're just summations of those things, right? Oh, I should know v1. Maybe that's that, right? Call it u1 and u2 because I've got vi's for two different things. Okay, but then you combine those things. This is f of summation alpha I plus beta I vi, right? But then by definition, this is summation alpha I plus beta I little f of vi, right? That's the definition of this capital F, right? And this is then summation. Now we unpack it in the other direction, alpha I f of vi, summation beta I f of vi. Okay. So we're just using our definition of f in reverse now, or actually we're using our distributivity, right, in reverse now. And this is f of u1, that was the u1 up there, plus, well, okay, sorry, let me just write it all out. This is f of summation alpha I vi plus f of summation beta I vi. This is f of plus f of u2. We're just sort of expanding, playing with the definitions and, putting things back together, right? So it preserves addition, preserving scalar multiplication is the same, right? A little bit easier. Okay. So I mean, this is super important, right? So if I wanted to find a map from, suppose I wanted to find a map from R3 to R15, well, 15 is to R7, right? And I just want to say, well, I'm gonna take 1, 2, 3, and I'm gonna map it to 0, 1, 3, 4, 9, 1, 2, 3, 4, 6, 7. Right? I'm gonna take 1, 0, 1. I'm gonna map it to 1, 1, 1, 1. There were 7 ones, right? So taking those two vectors from R3, I'm mapping them to those two vectors from R7. Well, then I get a unique, right? So these two things are coming out from R3. These two things are coming out from R7. So then I get a unique map, right? F, which extends this, going from the span of those two vectors that subspace, right, into R7. I just need to tell you where to send these two vectors, and the rest of the linear map's determined for free. And it's completely unique. There's only one unique map that does that, right? So turning things around, it says that any linear map is also completely determined by what it does to a basis, any basis, right? I would actually argue that. I have some linear map going from V, which is finite dimensional, to W, right? I take any basis at all, V1 through VK, basis for V. I define like little f of Vi is just f of Vi, that linear map right there. And now I apply my theorem and I say, well, I can extend this little f uniquely to a linear map. Okay. But when I extend it uniquely to a linear map, it's got to give me that back because that's a linear map that extended that. So any linear map going from V to W is completely determined by what it does to any basis. Sorry, hopefully you guys were hearing me. My thing was up here.
Yeah, we could still hear, but we had to turn the volume up.
Okay, sorry. You can say something. Good. All right. So I mean, this is a really important property, right? So usually we define linear maps, we define them on basis, and that's how we deal with them most of the time, right? And we're using this theorem all the time. Okay. By the way, can I always suppose this V is a finite dimensional vector space, and I have this S like this? Can I? So I guess I have these questions down here, right? So answering one of these questions down here, can I always extend this F to a function going all the way from? So let me just sort of like I've got F and it's going from S to W, right? S is this finite set, right? We've extended this uniquely to F, going from the span of S to W, right? Can I extend further to some G going all the way from V to W? And how would I do that? Now, remember, I'm assuming that V is finite dimensional. And we're assuming these are linearly independent, right? By the way, in the argument I gave above, now that I think about it, you should think, because I was a little bit sloppy here, where did I use the fact that things were linearly independent, right? It is used, right? So you ought to maybe think about that. It's not true. If they're not linearly independent, it's not true, right? I can't take two linearly dependent things and send them wherever I want and get a linear map, right? It just wouldn't work, right? Doesn't make sense. I mean, like I can't take something and it's negative and send them to two random places, right? And have the map be linear. But can I do this further extension? And what do I need to do? So, I mean, this is like a construction, right? This is like some of your homework problems. So I've got V1 through VK. This is sort of my basis for the span of S, right? So I'm using to define the span of S. This is a finite dimensional vector space. So what can I do to extend it the rest of the way out? Can I take this and extend it to a basis for V? Can I take any linearly independent set of vectors and extend them to a basis for V? If V's finite dimensional.
I feel like we can. I just don't know what the steps would be.
You don't have to actually do it. You just have to know it's possible, right? I mean, you don't actually do it. You just need to know it's possible. But this is the basic theorem that allowed us to discuss bases last time, right? I mean, the theorem in the book is exactly that. You can take any linearly independent set and extend it to a basis, right? As long as you're in a finite dimensional case, right? That's like the thing that allowed us to show things like every basis has the same size and stuff like that, right? So I mean, maybe review that part of the book again, right? That was last week's material, right? But yeah, you can do that, right? So you can take my favorite linearly independent set and I can go on and extend it the rest of the way to a basis for V, right? And I've got my map F, which is mapping these things into W. What can I do with those things? Does it matter what I do with them based on the theorem we just had? I can map them any way I want to, right? I can map them all to 0 of W if I want, right? Or any other vector that I want to, right? So I can take my F, right? So my F, which is going from S to W, and I can extend it to some like F prime, going from this whole set, let's call this S prime, this is a basis now, to W, right? And then I can take this F prime and extend it, whoops, other direction, to F prime, going from V, all of V to W, all right? And what I know about this F prime is it extends, you know, originally we had this map from span of S going into W, right? So this was our original F, this is our F prime, right? And this map extends this one. Because it's all defined the same way, right? We're just defining the function to be, you know, we look at the summate, we look at a linear combination, and we define the function like we did above, right? So for example, up here, right, I defined as a weird map, right, from some, by the way, what's the span of two vectors in R3? What does that look like geometrically? What is a two-dimensional subspace of R3 look like?
A plane?
It's a plane, right? So, I mean, the two-dimensional subspaces of R3 are exactly all the planes through the origin, right? That's what the planes are. And we extended this map, right, from a plane to R7 in this sort of weird way, right? Can I extend this to a linear map from R3 to R7? Isn't that what we just proved, right? Because I can take these two vectors, I can throw in a third one, something linearly independent from those two, right? So I have a basis for R3, and I can extend that any way I want, right? In fact, I could just map all those things to 0, right? So in particular, I could make that the null space, right? If I wanted to, of my new map, right? Because when I did this extension, I can take these things and map them anywhere I want to. I could map them all to 0, right? And then that would be the null space there, okay? Let me just stop for a second. Questions? I thought we'd move through this a little faster, but I feel like I'm pulling teeth here. No questions.
I guess I have a question. In the book, it used T to describe mapping and those functions. Are you just, instead of using T, are you using capital F?
You can use whatever letter you want to, right?
Okay.
Yeah. Okay. All right. So there's more algebra with linear maps. So what else can you do with them? So we've got our linear maps going from V to M, right? We know that these form a vector space, or not M. Let's call it W, because we don't use M much. All right. So this gives us some algebra of maps. We have a plus, right? We have scalar multiplication. All right, I can do L1 plus L2. I can do alpha L1. Okay, what other sorts of algebra can I do on these things? They are maps, right? So you know what you can do with functions. So what other sort of things can you do with functions?
Add and multiply.
So add we've got, right?
Uh-huh. And we've got multiply.
And what does multiply mean here? We don't have any multiplication in W, so we can't multiply in that sense. So what does multiplication mean here?
Scalar multiplication.
Well, no, we've already got that. I'm looking for new things, right? So suppose we have three
position functions.
Yeah, so the multiplication here is composition, right? So if I have like an S going from V to W and a T going from W to U, right? How do we define the product of these things? And what is the order? What do I define? Do I define ST or TS?
ST.
Actually, TS. I mean, it looks like it should be ST, right? But because we write left to right and we think of putting the inputs in here instead of in there, right? We actually flip those around, right? So we write like, because we do S first as a function and then T, right? So you have to be a little bit careful when using these pictures. You have to invert things when you compose, right? Yeah, but then this is defined. So this defines a kind of multiplication of functions, right? And so we would have TS of V, right? Is going to be T of S of V, right? So this is a thing in V, right? This is a thing in V. This is a thing in W, right? And this final thing is in U, right? Like that. This is a thing, you know, TS now is a thing in here, going all the way from there to there, right? It's a new thing, right? The composition of those two things. Okay. And you've got some you know, things that hold here. You've got associativity. All right. Yeah, I had all these to fill out these things, right? So here you'd say like, you know, TS. It'd be good for you to go through and fill all these things out, right? It's just T of S of V, right? Things like that. You have associativity, right? Here you need actually 4 different things, right? Because we have like V1 going to V2, going to V3, going to V4. It's useful to draw these little pictures, right? And I have here, I've got S1, S2, S3, right? And the order in which you have to combine these is reversed again, right? So it's like S3 of S2, whoops, of S2, you know, S1, right? So this is a product of 3 things. You only do products 2 at a time, so you have to combine them in some way. So you put a parentheses there, right? And then the associativity says it doesn't matter how you put the parentheses, right? So you get that. Okay, and somebody did that for their DQ. And I've already commented on it a couple of times, so I'll let you read that. And then you have a kind of distributivity, right? Same kind of thing. You got to make sure things are in the right place, right? So here I've got S1 and S2 going from W to U, and I have T going from U to V. So it's like that, right? It's in that order, right? And so when we combine things around, it becomes like T of S1. So all these things make sense. And T of S1 plus S2, like that, right? So all those 3 symbols make sense, right? They're all going from W to V, right? And you get this kind of distributivity. Right? Okay, and you get a kind of identity, right? If I have the identity, so again, you have to be a little bit careful. I have the identity going from V to V, and then I have T doing something, going to W, right? And so this is the identity of V, right? And so I have T identity V equals T. It just really just does T, right? And if I go the other way and I go from V to W, and I have T, and then I go identity of W, is still just going to go to W, right? And so this is going to be, and then I go all the way across, I just really get T back, right? So you get IW T is T, right? So you have these kind of two different identities here, like that, right? So you get a lot of algebra of these things, right? Of these linear transformations. And when you're looking at the same thing, you just have V, right? So we have, T and S. Let's take three things, right? Let's take S1, S2, S3, and LV. So their operator is just on one space, right? Then it kind of doesn't, you don't have to be as careful about the order anymore, right? Because now it's just everything's going from V to V, right? So the compositions also go from V to V. Right. So these so you get, usual same kind of thing, S1, S2, S3, is S1, S2, S3, whoops. S1, but here I can flip these around without having to worry about what I'm doing too much. All right, and we have S1 plus S2, right? I can do, I have to worry about where they're coming from and going to. You get all these sort of algebraic stuff going on, right? Okay. A lot of what you study in 513 will be rings. This is the ring of linear operators on V, right? So, we need to use it here too, but in the future, right, you'll sort of take this algebraic structure and study it even more, right? Does this look familiar to something else? Like if I had this kind of stuff? These are matrices, right? Okay, so there's going to be a strong connection, and actually this chapter already gets to it, between matrices and linear transformations, right? And so everything I'm proving here about linear transformations, those proofs will imply the same thing about matrices without having to do anything with indices and all that sort of messy stuff, right? We'll just use these facts about the linear transformations. Okay. Good. Any questions about that stuff? I'm assuming you've read this stuff, right? Supposed to have read, this just 2A, that's just 3A, right? So it's the very first section that we just got through here. And we're also about out of time. Now we've actually talked about the kernel. What is the kernel of the null space? It's a set of all what? So this is going from U to V, so it's a set of all U in U such that what happens? It's T here going from U to V.
That it gets mapped to 0.
Yep, T of U is 0. And this is the 0 of V if we want to make sure. All right. Is this a subspace? It is a subspace. How do you prove it's a subspace? What do I have to show? It's definitely a subset, right? It's a subset of U, right? So how do I show it's a subspace?
That has addition and multiplication.
Well, it has addition and multiplication because it inherits those from U. So when we're doing subspace, we need to show closure, right? So I need to take two things in here. I take a U1 and U2 in the kernel. Again, I use kernel and null, same thing. I need to show that U1 plus U2, right, is in the kernel. right? I mean, this is what we need to show, right? So, you put a question mark there. How do I get that? How do I know that U1 plus U2 is in the kernel? What do I need? So what does it mean to be in the kernel?
Everything in the kernel is 0, so it's just 0 plus 0 is 0, right?
Well, I mean, I don't know this yet. Remember, I'm trying to show this. So I need to show that U1 plus U2 is in the kernel. So I need to show that T of U1 plus T of plus U2, T of U1 plus U2 is 0. That's what I need to show, right? But T is linear, so T of U1 plus U2 is T of U1 plus T of U2. And this is in the kernel and that's in the kernel, right? So this is 0 plus 0, so that's 0, right? Okay, so U1 plus U2 is also in the kernel, right? Same kind of argument shows closure under scalar multiplication, right? Okay, so the null space of the kernel is a subspace. The image is just the set of all things. So how do I write the image? It's the set. Now, where's the image live? It lives in V, right? So the image is the set of all, T of U, right? Such that U is in U. Things that come from U, right? The image or the range, right? Is it a subspace? Okay, so we say it's a subspace. So I take two things in it, right? So I take V1 and V2. So these are living in V now, V1 and V2 in the range of T. Right? What do I know about V1 and V2? Well, they come from things in U, right? So I know V1 equals T of U1, V2 equals T of U2. I need to show that V1 plus V2 is T of something. What is it T of? Right, I know that. Now what can I do with T here? Since T is linear.
Can you factor it out?
I can, yeah, you can sort of say factor it out, right? I can use linearity. Right? So if U1 gets mapped to V1, U2 gets mapped to V2, then U1 plus U2 gets mapped to V1 plus V2. All right. So the range of T is closed under addition. Right? Same proof again works for scalar multiplication, right? You just do the same argument. Okay, so it's a subspace, right? T is injective if and only if the kernel is 0. Why is that true? So injective is 1-to-1 the same. So there's like two directions to prove, right? So T is 1-to-1 implies the kernel is 0. So how do I get the kernel 0 here? So assume T is 1-to-1, and let's say T of U equals 0. What do I need to show that the kernel is trivial? So U is in the kernel, right? I want to show the only thing in the kernel is 0, right? T is linear and it's 1-to-1, and T of U equals 0. So what can I say about U?
It's also 0.
It's also 0 because T of 0 is 0. And it's 1-to-1, so it's got to be 0, right? So U is equal to 0 since T of 0 is 0 and T is 1, right? So in the other direction, I'm assuming that the kernel is trivial, not 0, but the singleton 0, right? How do I show T is 1-to-1, right? We want to show T is 1-to-1. So what can I do? I can say, like, how do I show T is 1-to-1? What do I need to do? How would you show T is 1-to-1?
fundamental theorem of linear maps?
No, it's much easier than that. We haven't actually got there yet, right? I mean, if you're just like, what does it mean to be one-to-one? You need to take two things that get mapped to the same thing and show they're the same, right? Right. So, suppose this really is enough space, right? But suppose T of U is T of U prime. I don't run out of space and I just did something weird. I'm going to come over here and do it. Sorry. Suppose T of U is T of U prime, right? Okay. Remember, all I know is that the kernel is trivial. So what can I do about this? How can I use this? Can I like subtract? It's like solving an equation.
Can we use the U of 0? Like substitute the kernel in?
Oh, we need to use the kernel, but the question is how to use it correctly. So, I mean, what is this equivalent to?
Oh, could we do TU plus the kernel is equal to TU prime plus the kernel? Like have it like an additive or like the zero identity?
Maybe that's okay, but that's still maybe more complicated than what I want here. Can I look at this? Okay, and what can I do to the left-hand side? Because T is linear, what can I do to the left-hand side?
Factor T out.
Yep, I can do that. I mean, I like to say use linearity, but that's fine. You can say it like that. Okay, and what do I know about U minus U prime? Where does it live? Because it gets sent to 0.
It's in the kernel.
And what is the kernel? Remember, we're assuming the kernel is just 0, right? So U minus U prime equals 0. That's the only thing in the kernel, right? And so now we sort of undo what we did before. So we get U equals U prime, right? Okay. So if T of U equals T of U prime, then we get that U equals U prime, assuming the kernel's 0, right? Okay. So you get an if and only if, right? Okay, good. All right, and this is a good example of, I mean, this is a very simple if and only if proof, but you do need to prove both directions, right? So this is one of those things. This is used all the time. I mean, showing that the kernel's trivial is a very common way of showing that a map is injective, right? So that's usually don't try to show it's injective directly. Usually look at the kernel and see this. Okay.
Could you take a minute and talk about the test that's opening next week? Is that opening next week?
No, this is the second week.
No, topic 3.
Topic 3 has a test, but it's in week 4, right? So we're not there yet.
So it doesn't until week 4. Okay.
It's not till week 4. And I am meeting with the other guy to talk to him about what, because we haven't really decided what we're going to do for the 2 classes yet.
Oh, yeah.
So the answer is no for a couple of reasons. But that's,
yeah, I got
no, there's no test next week.
In topic 3, so okay.
Yeah, that's because of the way the university is. You can't have a separate. It's not the holiday. You just can't have a separate topic just for an exam, right? So we had to make topic 3 2 weeks long. We had to make topic 6 2 weeks long. But really, there's 1 week of topic, and then there's a week of exam, right? So that's really what's going on. So and I forget for you guys. Yeah, and where does Christmas fall for you? You may actually get that falling in between there somewhere, or it must be before Christmas, right? Yeah, it's right before Christmas, but you do get a week to catch up. Well, I guess it's not all the way until, yeah, you get a week before starting topic 6, right, to catch up a bit. Okay. Okay, so we're so pressed. So let me talk about the fundamental theorem. my voice is about dead. Look at these. There's a corollary here. Again, all this is in your text too, right? But you might look at this and try to fill this out based on reading your text. I think you might just take the PDF copy I sent you and try filling all this stuff out yourself, right? It'd be good practice. But let me talk quickly through the proof of the fundamental theorem, okay? So I'm going to leave it blank here. You try to fill out yourself, but you can, post this and post these sort of scratchy notes over here. So what this says is, it says, suppose V is a finite dimensional vector space, and we've got T going from V to W. We're not assuming W is finite dimensional. That doesn't actually come into this. This is linear. Okay, again, that's sort of implied when I write this. This is finite dimensional. Okay. Then what we get is we get 1. We get that the dimension of the range, or the image, is finite dimensional. And 2, we get that the dimension, this is what's usually just called this, right? Dimension of V is equal to the dimension of the null space plus the dimension of image. Right? So that's the theorem, right? So how do you prove this thing? Hold on just a second. Okay, right. So let's actually prove this thing here. How do we do this? Any ideas? How would you start this? You make me perform an awful lot here. Let's see. Okay, so I'm going to take a basis for the null space, right? Let me see. So this will be a basis. Okay. What else do I want to do? So I'm trying to get something about this. So this is a sub basis of, right? The null space is a subset of V here, right? Because the map is going from V. It's going from V to W, right? Okay, I want to get something about the dimension of V, right? So I've got these many vectors. This is an independent set. What can I do? I can extend that to a basis to all of V, right? So I'm going to take U1 through UK. I'm going to extend this UK plus 1. Say UN, say V is n-dimensional, right? This will be a basis for V. Okay. So what do I want? So this is the dimension, K is the dimension of the null space, because that's how that was chosen. I need to show that this is the dimension of the image. Right? That's what we need to do. So first of all, is all of the image going to be picked up by the range of this? So I take this thing here, take any V in, or let's say W, right? I'm going from V to W, right? So W and W, sorry, W in the image. Right? What do I know? I know that W is equal to some T of U, because that's what it means to be in the image, right? I know that U is written like this. This is going to be summation, some alpha I equals 1 to K of UI. That's the basis for the null space, plus summation alpha I equals K plus 1 to N VI. or UI, right? Because that's the rest of the basis I put in, right? Okay, but this is T of this part plus T of this part of alpha IUI, right? But where is this? This is in the null space, right? So this is actually just 0, right? Okay, so what we actually get is we get that this W is an image of just this stuff here, right? So that stuff maps, right? So T goes from the span of these guys to W, right? And in fact, it covers all the image, right? So it picks up the entire image when I do that, because that's what we just proved here. Okay, and so actually, so the span of T of UK plus 1, T of UN, is equal to the image of T. Okay, and remember, we're interested in a basis for the image of T, so wouldn't it be nice if that was a basis for the image of T, right? Okay, so is it the case that these guys here are linearly independent? It spans, it's giving me everything, right? Are these linearly independent? How do I show that something's linearly independent? I take an arbitrary linear combination, right? I look here at some alpha k plus 1, T of UK plus 1, plus dot, 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 plus alpha in T of UN equals 0, right? I need to show that alpha 1 through alpha n, or not alpha k plus 1 to alpha n are 0. That's what I need to show, right? I can factor out that T, right? I get T of alpha k plus 1, UK plus 1, alpha n UN is equal to 0, right? Okay, but what does that mean? That means this thing here, which is a linear combination of those vectors, is in the kernel, right? But if you look at how these were picked, right? There's the thing spanning the kernel. These are the other things linearly independent, right? The span of this set of stuff intersect the span of this is actually just the 0 vector, right? So this thing right here, it's in the kernel, but it's also in, I mean, so the point is this, that the kernel of T intersect the span. By the way, if you look at your homework, you really kind of done this already in the homework too. Right, so whatever the span of those things is, that is 0. In other words, another way of saying this is that the kernel of T plus the span of these things here, but I use the circle plus, right? So V kind of decomposes into the kernel together with the span of this other stuff, right? And so the point is this has to actually be 0, right? So alpha k plus 1, U1, UK plus 1, we're only doing those things, is actually equal to the 0 vector in V, right? But these are linearly independent, so alpha 1 equals, alpha 2 equals dot, 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 equals 0, right? They're all 0. And not alpha 1, alpha k plus 1. Which is what we needed to show, right? Okay, so it actually uses a couple of things I know you've seen in your homework. It's a nice construction. I did it really fast there. My voice is totally gone at this point. But you should think through this yourself again, right? Try to understand this construction here. Okay, and again, to your point, Austin, you're not constructing things in the sense of knowing exactly what you're doing, right? You're using theorems that say this and that thing exists. And so you're getting those things kind of for free, from some other theorem, right? You're not actually building them in some sort of way that you're getting your hands on stuff, right? Okay. All right, anyway, we're a little over time. Any questions? I should have more information about the exam next week because I'm talking to the other guy Wednesday is when I'm talking to him.